So yeah, let's talk about computer science outside of computer science, right? Because we're learning about like the hardcore stuff like logic and things like that the computer scientists, the software engineers use. There's plenty of biologists, right, using programming, using uh, purpose-made software to do some certain thing. So let's talk about that, because like this is the answer to this question is no, right? No, nobody's just like writing a bunch of turtle programs. What's that? Oh shoot! Thank you. Let me fix that. I didn't even notice. I saw it switch over. I'm glad it works. My bad. What's that? Uh, Thank you. Yeah, apparently the big computer gets priority, sadly, with the projector. So if it's on at all, it'll eventually take over. Yeah, man. Ooh, technology. All right, here we go. Let's talk about computer science and other disciplines, because nobody's just like making turtle programs all day long. This is a great way to learn computer science and learn programming, but like people in other fields, they've got their own programming language. They've got their own tools. And let's learn a little bit about that, let's say. I think I'm going to start us off with a question, actually. So let's think about social science and art. Some fields that aren't really, like, you're not using test tubes all day long. You're not really thinking about programming, are you? But computer science appears in these areas, don't they? Doesn't it? Let's think about that. So here's my first question for us. So please get into peer instruction groups, and I'd like you to elect a leader as usual, but write down, please, some examples of people using computer science to make art, for example. I think that's something we'll have some answers for immediately, right? And also like the humanities and social science, how are they doing things? I think they're doing studies and analyzing data, right? So what kind of software do you think they might be using? So what's some computer science in these areas? All right, let's see if we know. And I have some examples after that. All right, so take a little while, discuss with each other, like, what are we using? How has computer science made the field better? Oh, nice. Good thoughts. I hear good thoughts. Oh, I think I heard an interesting idea. What? Thought of that. Okay, another couple minutes or so to press submit. Oh, I thought of a relevant one. I'll have to remember to talk about that. Oh, God, that's way too loud. Is that enough time to talk about things? We may still be working on submitting. That's okay. I can ramble while you do that. But let's look. I think there's at least one group who's submitted so far. So nice. Let's take a look at group number 3. AI is big. It's a huge, huge deal, and everybody in every field is using it, right? So that's a great thought. Very good. AI robots that suddenly have expertise in any possible field. It's like a little somebody who can, like a researcher, a co-worker even. AI can be used for that these days. Could also use for data analytics. Yeah, everybody's got data and they're trying to analyze it. So that's a great thought. Yeah, so let's take a look at group 4, social science. Very good. Computers used to model things. Yeah, model the economy. A big thing that that I just realized is like we have the election tomorrow. I hope you guys have like voted early or planning on voting, right? People are throwing a lot of computers at analyzing the political landscape of the US, which is very surprising and cool, right? Interesting to think about. You can simulate stuff, you can analyze data. Data science is a whole new field that's coming up, and just like everybody's using a computer. So great thoughts, group 4. And then finally for art, digital art. People making digital art, they're using some program that was written by some programmers trained in art as well as computer science, which is really cool. Verify and analyze physical art. I like that. Yeah, have you guys seen 3D scans of sculptures? That's a thing. Is that what you guys are thinking of?
I was thinking, I know they used it to verify whether the painting was actually made by
Oh,
a certain painter.
yeah, that's a good thought too. And you can see the old, the things that were painted over. Yeah, yeah, that's really fancy. I love that.
Aren't they trying to use AI to old scripts that if you try and
Yeah,
read it,
yeah.
it's useful.
In such a way they can get an image, they can unroll the thing that you can't unroll. That's really, really cool. Yeah, so definitely look into all those things if you haven't heard of them. But those are great thoughts, great ideas. Awesome. Yeah, I think that's what I wanted to say there. Don't forget to do attendance if you have not. I'll stop that eventually. Yeah, these are good ideas, and art is an easy one, like Photoshop and stuff. So I just have a bunch of examples, and we'll go from there. All right. So one thing that I don't think we talked about, maybe AI kind of counts, is computational linguistics, which I talked a little bit about before. That's when this is a social science problem, I would say. It's when you have a computer and you're telling it to do something with human spoken languages, like human written text, for example, or even audio, stuff like that. So people are doing what? They're talking to Siri and Alexa all day long, right? Speech recognition is a huge, huge problem that has mostly been solved in our lifetimes, which is really, really cool to think about. Speech synthesis as well used to be a hard problem, also more or less solved because you have AI chatbots that can pretend they're Harry Potter and talk exactly with that accent, right? So that's really fancy these days that we've gotten that far. This is all under the realm of computational linguistics, I would say, and the kicker is natural language processing. That's when you're throwing a text at a computer and having it understand it. So NLP for short. And here's a quote that I stole from the internet. The ultimate objective of natural language processing is to read, decipher, understand, and make sense of human languages in a manner that is valuable. So AI could count as that. Just like analyzing all the text of Shakespeare in some way. People would use natural language processing to figure out who wrote which of the essays in the Federalist Papers, for example, those things. And like this is used all the time. In addition to ChatGPT, you've got like all these automated assistants on the internet. Like you're up at 3 a.m. and they're like, "Oh, hi, I'm an assistant. You can ask me a question," and usually they'll find you the right answer if it's a common enough question. And so they might not even be using AI, which is cool to think about. It's not a person, but they act like a person in a sense. And so we're familiar with that now. That's really cool. So yeah, some ideas in the social sciences realm. And let me try and break it down, like what needs to happen when you talk to your phone. Because like it's wild to break it all down and think about what's really going on under the hood. A lot has to take place, a lot of separate steps. Okay, so the first thing, like Siri, for example, it's a natural language processing tool. What does it do when you talk to it? You say, "Hey Siri, set a timer for 5 minutes," right? Something like that. That's a thing that people do. The very first step is you have just emitted sound waves, right? You get that through the microphone and somehow understand what was said. So the very first step is going from voice to text, which is not obvious, I would say, right? So the very first thing is speech recognition is what Siri does, what Google whatever does. So you have to convert all this into, like, even if you had an accent, for example, get it to the right text. "Hey Siri, set a timer for 5 minutes." Right? So that's one big step, right? That's not at all obvious. You're going from voice somehow through a computer to text. And then, all right, now that you have text, you can break down the text. Okay? So what do you do there? So you've got to like notice patterns of things. Like notice all of these words together. Like "Hey Siri" together, right? Those two words, one after the other, those tell it to wake up and like pay attention now. Like that's an activation step, right? So you have to hook into that. Like you have to parse the text in a way like you kind of learned how to do that in elementary school maybe. It's like now, like what do you want to do? What is Siri like? What is it listening for? What is it trying to accomplish? Well, set, that's a verb, right? Set what? A timer. There's your object, right? And then like for 5 minutes, that's like a duration, let's say. It's modifying the verb and the object in a way. So like you have to parse that sentence in that way. Does that make sense? Like that's happening under the hood somewhere. This was working pre large language models and AI, so they were doing this in a different way. They were doing this kind of breakdown, and it understands what you meant one way or another. So it's like verb, object. It's trying to figure out what you want, and then it can go off and like once it's done that and parsed your sentences, so voice, your speech to text, to parsed text, understanding the intermingling of all the words, then you can finally go and like do what you need to do. Okay, set a timer. I understand how to do that as Siri. And then, okay, what does the timer need? What argument does the timer function take? Like it takes a duration. There it is, 5 minutes. I have everything I need to accomplish this task now, right? And it goes off and controls your phone. So that's natural language processing in a nutshell. It's a very powerful idea. It's really, really cool that we have all these steps working together to achieve a goal. And this is just like, this has come of age in our lifetimes, which is really cool that we get to experience it. Okay. Another field of social science, I would say, is human-computer interaction. It is something that you can study in grad school. It's more of like an advanced topic of computer science, I would say. It's just studying like the way that you can, like humans interact with devices and computers. Okay. So it just studies that, the interfaces between humans and computers. And you've seen like cats playing games on iPads too. So some of those interfaces work for things that are not humans, for animals that are not humans too. So that's kind of cool. But yeah, you have human-computer interaction researchers to thank for like graphical user interfaces, or GUIs for short. Like back in the day, do we know this? Like all a computer was just a bunch of text on a screen. Before screens, it was just all printed out. Have we seen that? Have we understood that we've come so far? Do we know that? so for example, if you take CSCI 40, you'll learn that in a sense. But like this is what the computer used to look like back in the day, and this was like printed out. Like you give it little commands, and it like understands those commands, and it's all text based. So that's what the first computers were all about. And then eventually, human computer interaction researchers were like, I think there's probably an easier way. And once computers got a little bit more powerful, they started inventing like, all right, let's try and make it so like this looks like somebody's desk, and like you've got papers on the desk and you're moving them around. And so suddenly you have windows, right? So it started out as a bunch of text. Let's write that there. And then you have a bunch of windows that you can, that are each displaying something. You can move them around and like have them overlap too. So windows. And then, of course, you needed a mouse, and somebody had to invent a mouse. It was invented by Xerox, of all companies. Do we know that? The copier company had some really, really good research and development people, and they invented graphical user interfaces as well as like the mouse, which is wild. And then they didn't know how to market it very well, and so they gave all their ideas to Apple. And then Microsoft stole from Apple. So it's all just a bunch of people stealing from each other, honestly. So that gave rise to what we have today. And nowadays we've gone even further than that, right? We don't just have windows on a screen anymore. We have like people playing Pokemon Go, don't we? We have like virtual reality, we have augmented reality, and the headsets are very clunky right now, but eventually maybe like we'll just throw on some glasses and that will be our computer, and it walks with us all day long, right? Isn't that wild? So it's fun to think about these things. Do we have any comments, any ideas, thoughts about any of that? That may be where we're headed. Pokemon Go, for example, is a good example of augmented reality, right? And so just like think, if you've played Pokemon Go, like what has to go on for it to like keep the Pikachu there and like have it like be displayed? It has to do some computation, right? Any augmented reality, virtual reality software, it's got to find the horizon. It's got to know where Pikachu can be. It's got to like notice the terrain in a sense, like put him like, are you standing on a hill or something? It's got to look kind of normal. It's got to figure all that out from your camera, which is cool. And so that may be where we're headed as far as interacting with computers is concerned. And if you're interested in that kind of stuff, study this topic, human-computer interaction. All right. So that's fun examples today, I would say. And now let's get to art. So you got like physical art, you've got music. So just like anybody who has listened to music in the modern age has computers and computer scientists to thank for, right? We're not just all recording stuff on tapes anymore. Everybody's recording through some sort of software, most likely. All right, and especially if you like something that doesn't use normal instruments, like if you like electronic music, then obviously you have computers that are producing that. It was Yamaha, apparently, the company that makes everything. Back in 1974, they made the first digital synthesizer, and so like that's of course bled into so many different genres, and it's like defined the electronic music genre. It's amazing to think about that. So like it's like a few decades, and we have a new kind of music. And like everybody's using software nowadays to record their music. You've got, if you're not a pro, you got like GarageBand on a Mac or something, and like more professional softwares like Logic Pro, Ableton Live, if you've heard of those things. But like nowadays, like you can produce your music by plugging in your instruments to a computer. There's a lot of artists who got big doing that, and that's really cool that you don't have to go to a studio anymore. It's really opened up the field, I would say. You can plug your guitar legitimately into your computer. My best example of an electric guitar, and like the cable is definitely going in the wrong spot there. So that's kind of neat. All right, and then you can use software to like pretend that you really were recording your guitar in a large studio. You can simulate the effects of like reverberation, reverb, right? The what's it called? Like fancy amps, the echoing of the walls in the fake studio, all that stuff. You can make it sound like you plugged into a really expensive amp, and they use machine learning to learn how to like turn your guitar signal into the computer into acting like that particular famous amp, which is really cool, right? So that's a thing, right? That's that's something you could specialize in one day. Like, these are your options as a computer scientist, because all of these fields need one of you, right? Somebody who knows how to program and knows some other idea as well, some other field. And they come together, okay? And then digital art, you guys talked about that. That's a huge one as well, right? So let's see here. You can do two-dimensional art, of course, right? You got Photoshop, and you can also do three-dimensional art, right? I heard this quote on like probably Reddit or Hacker News or something, but somebody said like the best composers of our time are probably writing music for movies because that's where the money is, right? And just like the famous composers of 100 years ago, they were writing like concertos and people actually went to them. Nowadays, it's probably people are writing music scores, and that's where the famous people are, the best people are. And then they said that the best artists are probably like painting digitally in Photoshop or like working for a game company, something like that, which is maybe true because that's where the money is, right? So there's a lot of very, very fancy people who are working completely digitally these days. They can be making stuff in Photoshop. That's two-dimensional art, right? Virtual brushes and all that. You'll be talking about that in your essay, right? And yeah, that's just like how they can reach the most audience, I would say. So that's kind of interesting. And then there's also 3D artwork, which is huge for definitely video games, movies as well, any sort of like graphics, which is fun. So 3D artwork is huge. There's a nice open source program called Blender where you can like make your own things. It's a free program. You can learn it, and you can like sculpt virtually on a computer with a little virtual tablet pen. You press harder and it like digs into the virtual clay. And it's like people are doing that these days. That's really, really cool. And like, again, that's something that you could specialize in. If you know a little bit about that, you could go that route. And it's good to find a niche, I would say. Okay. Any questions, comments about that? So that's one area that I wanted to talk about. Social science and art. Like, it's not just a bunch of people writing programs that add up a bunch of numbers, right? There's more to it. So I wanted to show you the big picture today. Now, let's go to the field of the sciences, the harder sciences, medicine as well, like chemistry, biology, physics, all that fun stuff. Think about these fields now, and think about where people are using computers. I would think that they've taken over quite a bit more in these fields. So go back to your group, please, and I'll stop attendance after you do it. But please go back to your group. I won't, if you want to just like, if you're on the same page, you can like keep your stuff and overwrite it, or you can write a new one, doesn't matter. But please write down some examples of computer science this time in medicine, hard sciences like biology and chemistry and physics. It might be easier to come up with examples this time. I'll give you a few minutes. Yes. Another couple minutes to press submit. Alright, is that enough time to get something in? I'll ramble until you press submit then. Alright. Yeah, I think we moved down. So, thank you, group number 5. Let's take a look at what you said there and go from there. So, okay, yeah, like gene editing. This is great. That's a great example of computer science being used in, what is that? Would that be biology, I guess? Yeah. We all heard of CRISPR. It's when like you're editing the genes, I think, right? Which is really, really cool. And then, yeah, a lot of cool chemistry stuff as well. Like you can simulate reactions. I think I have a slide about something similar to that. And yeah, nowadays, like even radiology, you're getting X-rays taken. They all appear on a computer these days. So they're not using the X-ray film anymore. More or less, at least, which is nice to think about. So I guess maybe that saves something, saves the planet a little bit more to do it that way. But yeah, computers have definitely taken over, I would say, in the sciences and in medicine. So let's take a look at group 4. Nice. Yeah, you guys got a lot of good examples here. Medical scans, just producing, medication. You can like do some simulations to like figure out what's going to attack the virus in the right way once you have it all. Just like getting the DNA of the virus as well. Good thoughts there. Like that takes a computer. Like you can't have a person like, okay, that's an A, G, to take like many lifetimes to figure out all that without the help of some software to figure out like what's the sequence of DNA that we need to like look into because like that's the DNA of the virus or whatever. So yeah, good. Robots doing surgery, like even people doing surgery virtually, like somebody in a different country is like operating on somebody through the help of a robot. That's really cool. A pacemaker is a great example. Like that's an old school example as well. Like that's been around for quite a while, and like it was one of the first good examples of like you're putting a computer in somebody's heart, and like that's gonna help them. So great thoughts. Yeah, all that fun stuff. Microscopes, radar, any kind of simulations, good. Like just any plane these days up in the air is using some sort of aviation software to help it. What is power distro? I haven't heard of that. Oh, yeah, I understand. Yeah. It's like trying to keep everybody's house powered. I like it. And yeah, just like doing anything with nuclear or anything. Just like trying to keep it all at the right temperature, all contained. Very, very good. Yeah, all the different like the large colliders in Switzerland or whatever, like trying to learn stuff about the nature of the universe by using a computer to shove particles very fast into each other. So yeah, those are great thoughts. Good job. Good examples. I think I have a few slides with what you said. Like you guys got most of what I said, I think, and then I have some more. I do believe. So nice. I promise to stop that. Let's get out of there. And yeah, let's just walk through some examples again today, just to give you a zoomed out perspective, because maybe you're down in the weeds, like dealing with turtles right now, and you don't really understand like what's going on in the real world. This is what today is for. So yeah, some good examples that you guys didn't talk about. One is weather forecasting, which is very near and dear to our heart as Fresnans, right? You want to know, can I go outside right now or will I melt? So, all right, how can you do weather predictions? How do you do that? Let's think about it. Right? You can simulate. The answer is to make a simulation. You can model like the air and the atmosphere and the clouds and all that stuff using fancy physics fluid dynamics equations and also thermodynamics equations. So like you learn about those in a physics class, and you can apply them. You can simulate them on a large scale. All right, so that's really cool, right? So what you do is you put a bunch of sensors around Fresno, for example, and you have a bunch of computer, or you have some supercomputer that you give all this data to, but you can make some pretty accurate predictions based on it. So the idea is like you've got, at time A, you got a bunch of sensors throughout the city, or you've got radar from a satellite that tells you like here's a rectangular prism of Fresno air. All right, and like you got a bunch of sensors, or you got radar data from a satellite telling you what's going on. Like here's the pressure right here at this point. Here is the temperature at this point. All that fun stuff. Here's the humidity. Here's the way the wind is blowing and all that. So you take all this information at time A, and the whole job of a weather forecast is to, at time B, using this as a starting point, figure out how it's going to change. Like, all right, at those same points, what is going to be the temperature, the pressure, the humidity, all that fun stuff. Does that kind of make sense? That's at a basic level, that's what forecasting is. It's a simulation of, all right, here's what I know right now. How is it going to change given like what I know, the way the wind is blowing, what the current temperature is, like whether or not the sun's coming up or going down, because that'll cool things off or heat things up, right? All that stuff you have to consider. And like you can build a very large like supercomputer program to like try and figure it out. And all these physics equations, like you can't model every atom of air inside of a computer, and so you have to like, what's the word? You have to simplify your models, and so that leads to errors that compound. Unfortunately, it's like the weather data for like 2 weeks from now is not as good and set in stone as like the weather forecast for a week from now. Like we're better at that. The shorter the time period is. So like farther in the future, you try to predict like what's going to happen. The more just like randomness takes over, and like the simplifications that you've made in your simulations, they kind of like ruin stuff. Okay, so yeah, it's not the weather person's fault. It's just the fact that they didn't have enough sensors out in Fresno or enough supercomputers to run the data better. So that's kind of nice to think about. So that's a fun little idea, I would say. Like that can be a career for somebody, like designing the weather forecasting models, which is really fun to think about. So yeah, consider that. There's also on the same vein, you got air quality in the valley is horrible, and so people forecast that as well. It's the same idea. Like, all right, given the air quality right now, what I know, like, is it rush hour? Is the sun really hot, making extra ozone or whatever? Like, what is the air quality going to be an hour from now? Stuff like that. And one fun thing, if you follow the air quality forecast like I was, like a few years ago when we had all those like tons of wildfires at once, you remember those days? Had to stay inside. Like the air quality forecast said tomorrow it's going to be like 10 times worse or something horrible, because like the model had never seen air this bad. It's like, all right, if it's this bad right now and it used to be okay, it must be getting worse. Like that's what the model thought. It could be thrown off by unprecedented stuff, which is really interesting to think about, because like when you're training something with machine learning, for example, like it's making, like you're trying to teach something how to work. You're teaching your weather forecast, your air quality model based on like, all right, this is how it used to be. This is like how things progressed back in the day. Learn from that. And it was making predictions based on what it learned, and it just like suddenly you give it something that's unprecedented, like so much bad air, so many fires all around us, and it just thought like the world's going to end. Like the air quality is going to be 10 times worse than any other place on Earth, for example. And it didn't come to that. So yeah, that shows you that there's still work to be done. Okay. And yeah, I think the last thing, speaking of fires, like you can do simulations of how fires are going to play out, and that's what firefighters are using all day long when a big one breaks out. Because you can predict the way that the fire is going to travel, right? Like here's the current boundary of the fire. You can, with weather data as well, simulate what's going to happen to this fire. Like you can like plug in like this is the type of brush over here is very flammable, maybe not so flammable over here, or like the wind speed is really going in that direction, stuff like that. And so you can simulate like, all right, tomorrow this is what's going to happen to the fire, and we should focus on this part or something. So that's really, really cool, and that gives you a better chance at like saving people and their property. And computers are at the heart of it all. Okay, so I like that. It's a fun idea, and I hope that makes enough sense. Thoughts, questions about any of that? Comments? I think I had a friend who went and got a PhD in something along these lines, and so it's something you can do. It's really cool. All right, let's next talk about the genome and genome sequencing. So that's one thing that you guys wrote down already, but let's talk about it some more. Yeah, you need a computer to obtain DNA samples. Like you cannot have a human just counting all the base pairs and all that, because that would take forever. All right, so a really, really cool, huge success of computers was in 2007. I'm sure we were all probably, most of us were too young to remember it, but that was the time that we have made the first sequence of human DNA. We took somebody's DNA and we extracted all of the base pairs. Like this was A, T, C, G, A, whatever it was. All right, dot, dot, dot. There were lots of them. All right, and that took a while, and like that was a huge success. Everybody loved that. And it was a good combination of computer science to do the analysis, plus engineering to just make the tools, the physical tools that you need to actually get that stuff out of like somebody's DNA, which is fun to think about. And so that was back in 2007. Also in 2007, this company that just went under and went bankrupt, right? Have we heard about that? 23andMe, they're going bankrupt. I think I heard that. And so everybody is on the internet is like up in arms because now they're worried that all their data is going to be sold to somebody. And so if you've done, has any of us tried 23andMe? Oh, nice. Yeah, it tells you a lot of really cool information about like your background, like where your DNA comes from in the world, like your ancestry, as well as like it will also look at and see like if any of your DNA matches like genetic genetic illnesses and stuff like that. So it can help you stay healthy as well. So yeah, do consider deleting your data if you've done this once you get it, once you print it all out. But I think they're going bankrupt, and people are worried about like they have all this data on you. Whoever buys that might not be as big on privacy as they were. So that's something to worry about nowadays. So they also started in 2007, surprisingly, and this is a lot cheaper. It's very, very expensive to get the entire person's DNA, but it's cheap to do this kind of ancestry testing and like disease risk testing. There's a little bit of a difference. So what the 23andMe people do, they don't sequence your entire genome. That would cost millions of dollars. Instead, they cut it up into pieces, essentially, and they have like a reference piece. So like, all right, here's your data. Like here's your DNA, and they've got little pieces that like would want to hook onto that, and they go and check like, okay, this data means that you come from like Northern Africa or like Western Europe or something, and like this piece of data means that you have this genetic disease predisposition. This piece of base pair, like it'll go and look for little chunks to see like, okay, this means Western Europe or something, and then it can like draw a little map and tell you this is where you come from. Like there's Spain, Italy, the UK, Ireland, Africa, and they have a bunch of data. They've gotten a bunch of little chunks of DNA from people with all these kinds of ancestry, like here in Africa, here in Western, Eastern Europe, all that stuff, Northern Europe, all that fun stuff. And then they can compare. They can compare you to them, and so they can tell you like, oh, you're this percentage North African, this percentage Western European, that kind of fun stuff, which is cool to think about. But they're just looking for little chunks of DNA, and so that's why it's cheaper, as well as it happened around the same time, right? But yeah, consider the privacy implications of giving your DNA to somebody, though. I think that's important to worry about and wonder about. So yeah, I still haven't done it. Maybe one day. What next? What next? Let's talk about robots. Robots being used in medicine, or being given to people, even robotic appendages. And so there was a fun breakthrough a few years ago, 2019, that I want to talk about. All right, this is a good example of computer science as well as engineering in medicine. And so read the article if you'd like. But here's the idea of robotic. Let's talk about robotic arms as well as prosthetic arms, because there is a difference, and I didn't know the difference until I read about it more. So there are people who need a prosthetic arm, and there are people who need a robotic arm. And let me try and help you understand the difference. So the idea of, like, if you have an arm and you move it, you're sending data from your brain, right? Your brain is like, I think I want to move my arm, and then it tells a part of your brain, the motor cortex apparently, do the movement, and it sends the signal down your spinal cord, eventually into your arm, and like it moves, right? And so that's in an undamaged body. If you have a prosthetic arm, you need a prosthesis. If you don't have an arm, they hook it in, and like here's how a prosthetic arm works. You've still got a good spinal cord. You're still thinking in the right way to send the information down to the arm, but you don't have an arm anymore. And so like the signal can be hooked in at the arm level. That's what a prosthetic arm is about. You can hook it in at the arm, get the signals from the nerves right there, and that will be used. You can train that to like move the prosthetic arm. So that's what a prosthetic arm is. You can hook in down at the arm level. Like, that's fine. The signal is still getting there to move it. Okay. For a robotic arm, the difference is the signal doesn't get to the arm anymore. Okay, so for a robotic arm, there's something wrong with the path through usually the spinal cord to get the information about, I want to move this arm down to the actual arm. And so they have to hook in instead into the brain. Okay, that's the difference, where they hook in for a robotic arm versus a prosthetic arm. So they hook in into the brain, and then like they take the signal's still good up there, and then they hook that into the robotic arm, and then it gets moved. Okay, so that's the difference between a prosthetic arm and a robotic arm. And they used to have to do some sort of invasive surgery, like to get the wires in the right spot. It wasn't fun, I don't think, for anybody. And so a very cool new thing that happened in 2019 was they made a non-invasive robotic arm. They just put stuff on your head. Maybe they had to shave your head or something, I don't remember. But they didn't have to like drill into your skull or anything, which is very nice. You just need to put a bunch of sensors on the head, and then you can read the activity of the person's brain, and that will move the robotic arm. And like that's a huge, huge breakthrough, obviously, for anybody who needs that, I would say. And so that's a really, really powerful idea, right? You've got people whose quality of life is hugely improved thanks to computer science and engineering, right? Any questions, thoughts about that? So that's just fun to think about in medicine, I would say. Nice, nice, nice. Let's see, what else do I have for the day? Coming from Fresno, let's also talk about farms, right? Farmers are making smart farms these days, which is crazy. So what can you do if you're a farmer? Maybe some of you do come from farming families. So a farmer, you can put a bunch of sensors around your field, first of all, that like monitor what's going on. Like, here's your field. You don't have to go out there and take samples. You can just like put some stuff in the ground, and it will just like be connected to some mesh network and hook into your house, and like you're getting the signal. It all works out. So here's your house. You comfortably sitting in your house as the farmer, like some satellite dish or something, getting readings from your sensors. You get to know when to do stuff, when you need to water and stuff like that. So that's really cool. Like monitor how wet the soil is, for example. And you can stick a bunch of those out there, and you don't have to go out as often anymore. You don't have to do as much work as a farmer, which is nice. Another very cool thing is self-driving cars still suck, right? They have not been. It's not a solved problem. Self-driving tractors, though, completely solved problem. Easy. You can make self-driving tractors all day long, and farmers have these. So imagine, right? It's so much easier to make a self-driving tractor because all you have to do is hook a GPS onto the thing, tell it the corners of your plot of land that you want it to plow or whatever, and then it can just go forward and back, right? It can deal with that. It does not have to have any sensors anywhere, really, because there's no humans, right, walking around. Like, hopefully you gate off your farm or something, but like you don't have to do any weird recognitions of stoplights, of people even. Like there's nobody to hit. Nobody's going to be walking on your farm. It's their fault, right? If they were trespassing. You don't have to obey any traffic rules. So like self-driving tractors are a thing. It's a completely solved problem, which is really fun. Very well-defined boundaries of your plot of land that you want to go through. As long as the GPS satellite doesn't get jammed by one of our enemies or something, you're good. Yeah, maybe it has a fail-safe and the tractor will stop if it ever loses the GPS signal anyway. Like it's not going to hurt anybody or anything. So that's really cool. Okay. And yeah, finally, like big data is a thing, like the idea of doing data analysis of all of these sensors that you've now shoved into your ground. You can make predictions based on what you see there, right? You can be like, okay, the water level's at this right now. I know based on previous data how fast my crops drink up that water. And so I know for like to save myself the most money and keep my crops as watered as possible, I will wait like 3.5 hours before I turn on the sprinklers again or something. Like you can do that kind of thing and do that kind of analysis to save you money, which is really nice, right? You can make better predictions from all the sensors. They're just giving you data all day long. Okay, so like big data is a thing now. I don't really like that term, but like that's what is applying here. Okay. Any thoughts about that? Or are any of us farmers?
But I work
Oh yeah.
in a similar vein to what you're explaining.
Oh yeah. Nice.
I work for a company where they do sell fertilizer, so they have a box that keeps track of the pH levels, all the
Nice.
nutrients in the ground,
Yeah.
and depending on what crop they're going to feed, there's a certain amount of nutrients that needs to be fed.
Exactly.
And they have a time span, and so they have this much they want to feed, this how, and how much water they want to feed, so to see how diluted it's going to be.
That's super nice, and that's so much better than like you're saving a lot of money. You don't have to employ people to go out and take the samples.
Feeding just a huge trunkload of fertilizer, let's say nitrogen,
Yeah.
micros, and instead of just dumping it, you precise feed it.
Mhm.
So you save money on just the amount spent.
You know exactly how much you need at a better granularity. Yeah. Awesome. That's really cool. That's really nice to think about, and yeah, your livelihood is connected to this in a way. I like that. Awesome. So yeah, let's go somewhere else. Let's go into space now. For my last two slides, everything we've done in space, right? This needed computer science from the very first lunar lander. I showed you the real cool picture of the woman who led the team who designed the lunar lander software, like a huge printout that was almost as tall as her, right? That was super cool. And so like we needed software to do any of that. Like all the satellites up in the air, software, right? Everything in space is made possible thanks to computer scientists and computer engineers, all that fun stuff, all right? So telescopes are a big one. Like that was maybe the first example because like those existed before we could make satellites. Maybe like first of all, let's say like we've got a telescope on some high mountain, say in South America. There's South America, and we want it to look at a star, right? If you like before computer days, like the Earth is moving, the galaxies are moving, and so you have to keep it focused very tightly on what you want to look at. Whereas nowadays you can be like, all right, you know what? Just point at that star and never lose it. You can have software keep track of that now. It's really cool. All right. You also have space telescopes, of course. Like just sending anything into space, first of all, takes a bunch of computation. Like you've got these, like that new huge telescope from NASA, for example. Like it can position itself, look at some galaxy or some cool thing in space, and it can just stay locked on that, and you can program it to do that, which is really cool. All right. Of course, yeah, just satellites doing other things. Like you've got GPS, among others. Right. Plenty of satellites doing very fun stuff for us. Even our phones can connect to satellites, some of them these days. And you've also got all the rovers, right? All the unmanned things that we've sent to different places. Like you've got those Voyager probes. You've got the landers on like the moon from, I think it was China that landed, or maybe India that landed the most recent one. I can't remember. And then the one that we landed on Mars. like that is solar power. It's got a bunch of sensors. It's all computer based, right? And people are reprogramming it to do new things on the fly as like pieces of it break. It's really, really cool to think about. Okay. And yeah, so like everything we've done in space that has like affected us very, very nicely, like GPS, we get out of that, out of that deal. We have computers to thank, and so that's an area you can go into if you like computer science. And I think the last thing I want to show you is maybe the most, depends on who you ask, but this could be one of the most important things, one of the most important discoveries we've made recently. Have any of us heard of what's called protein folding? It's a weird term, I know, but it is a very, very cool one. Once I explain it, you might want to look into it further. So what protein folding is all about is, by the way, I'm not a biologist. I am not good at explaining this very well, but I'm going to do my best. Here's a picture to help. Apparently, proteins, they're made up of amino acids, right? Maybe we knew that, maybe we didn't. I don't know. It's been a while since I took biology. Maybe same for you. So proteins are made up of amino acids, and the order of those amino acids, just a big long chain of amino acids, the order of those wants to bend, apparently. Three-dimensional bend and curl up and do weird things. Okay, so like your cells are making these chains of amino acids that are proteins, and they like to bend and curl up in a weird way just based on the order of those things. I don't understand it, but that's what happens, right? And they can curl and do weird things, and that's how they interact inside of your body. Like certain proteins want to do one thing because they're curled in that way to want to go there, essentially, right? That's the idea. And so the interaction of proteins is essentially medicine, right? The whole job of you making a medicine is to interact with the proteins inside your body in such a way to make you better, right? To do something like that. And so if we can come up with new chains of amino acids, new proteins, and figure out how they're going to twirl in such a way that we have some other protein that we want them to attack, for example, and like envelop, we can model that inside of a computer now. That is the new thing, right? Protein folding via machine learning, right? People use machine learning to great success to figure out how these proteins will fold up and how they will therefore interact with other proteins. And that can be used to make medicine. So AlphaFold 2 came out in 2020. It's a machine learning model, I think, by people at Google, researchers at Google, and it can predict the structure of proteins, right? They're going to fold in their weird shapes, and that's how they interact with other things, as well as like all the viruses, right, is some weird proteins. We want to like deal with those. Some cancers even, right? So making weird proteins. So AlphaFold 2 blew every other machine learning protein folding technique out of the water. It was like, I don't know, maybe like 70% accuracy, 80%. It was like much, much better than like the 40% that the ones before it were doing. Still not perfect, but it's getting there. I think they've made more progress since then, of course. But like, it got really good, and they actually thought that they were cheating it was like a bunch of it was a big competition. Like everybody sent in their model, and they all competed. And this one got so good that they thought they cheated, and so they gave it something that only researchers knew what it did. Like they fed it into the model, like they had never seen it before, and they still got it right. They predicted it's folding correctly, which is really, really cool. And this will lead to us living longer, probably. It will just help humans in a very cool way. The better you can predict how your protein's going to fold, better you can understand like how it's going to interact inside of a cell, the better you can understand cells, the better you can understand like whole biological systems, right? And make medicines to specifically target something that's wrong, which is really, really cool, all right? And so it will help make us healthy, and this is a very, very cool area of current research, okay? So yeah, all today was, as the sun is now down, all today was just a bunch of examples to show you like what you could do as a computer scientist, because maybe like you don't understand the big picture because I'm just giving you turtle stuff to do right now. There is plenty more outside of hardcore programming like this, okay, that you could maybe one day fall in love with. Yeah, any questions or comments about any of this? I think that's all that I wanted to talk about today. Yeah, so that is computer science and other disciplines. We are not done. There are more disciplines, but that's as much as I want to talk about, at least for today. Okay, so yeah, we'll come back and have a programming lecture next time, and I'll also give you an extra credit but no new assignments today. So that's all that I would like to record.